All right, good morning, everybody. Thank you for inviting me, to the organizers and to the attendees for coming on a Friday morning, after a long week. I have to tell you, I probably am the person who, in the room, who knows the least about quantum physics and quantum information processing, quantum computing, but I might be somewhere near the top of what I know about lattices in this room. So what I'd like to do is tell you, transfer some of that knowledge about lattices, and I hope throughout the day you'll be able to transfer some knowledge about quantum to me, and it'll be a good exchange. So thank you, everybody, for being here and for inviting me. So I'd like to tell you about lattice-based cryptography, what's been going on in the theory and practice of this topic. There's been a lot of work over the past 10 years, and then especially over the past 3 or 4 years. So I won't be able to cover everything for sure, but just to give you a flavor of what's involved in this area, this very exciting area. Oops. So let me go back. Yeah. Okay. So the agenda roughly for today, I'd like to first talk about the theoretical foundations, tell you what lattice problems are, what lattices are, and what the problems are that we usually work on, and define 2 special problems called SIS, short integer solution, and learning with errors that have many applications in cryptography. And then I'll talk about some ideas to give higher efficiency to lattice-based crypto using what are called rings, polynomial rings, and some of the schemes and problems related to those, like NTRU, the ring versions of SIS, LWE, and their connections to what are called ideal lattices in rings. And I'll mention toward the end the state of the art, or maybe even not the state of the art, but the state as of at least a year or 2 ago in terms of practical implementations, schemes with catchy names like Bliss, New Hope, Frodo, HElib, however you pronounce this, and so forth. And then along the way, I'll give some open questions, research directions, things that perhaps you as quantum type people can help us with. Okay, so we'll start out with the foundations. So what's the big idea behind lattice-based cryptography? So for the past 40-ish years, we have had public key cryptography, starting with Diffie-Hellman, RSA, and that explosion that these papers and works unleashed onto the world. And all of this cryptography, this public key cryptography, has, for the large part, been based on number-theoretic mathematics, like the factorization problem, modular exponentiation of various forms, bilinear pairings on elliptic curve groups, and so forth. And so the idea behind lattice cryptography is to replace those kinds of mathematics with hard problems on lattices, or at least, if not replace, augment. Okay, and so these are completely different kinds of mathematics with different geometrical structures, different kinds of problems, and so forth. But it turns out that we can use them to allow Alice and Bob and anybody else who wants to do cryptography securely to do so against attackers. So why should we want to do this? Well, first, the schemes that we get tend to actually be quite efficient. They involve linear operations, not complex exponentiations on huge numbers, but rather linear operations like multiplications and additions on relatively small numbers. And these operations are also embarrassingly parallel. They involve things like matrix vector multiplication and fast Fourier transforms, things like this. So we get quite good efficiency. Most of the schemes are conjectured to resist quantum attacks. So that is, these are classical schemes that can run on your computers today, but we believe, at least the evidence suggests so far, that quantum attackers will not be able to break such schemes, even using the full power of quantum computation were it to be realized in practice. And that's in contrast, of course, to the situation with things like factorization and discrete log systems, where Shor's algorithm completely breaks these schemes on quantum computers. So we don't know that these are secure against quantum attacks. We don't even know that they're secure against classical attacks. That goes for all cryptography. But the evidence so far, people have attempted to use quantum algorithms and so far have not come up with much. There's a nice theoretical advantage of lattice cryptography in that we can get strong security guarantees based on what are known as worst-case complexity assumptions. And we'll talk more about this in a few moments. But basically, the idea is that for cryptography, you need your schemes to be hard to break for the random choice of keys or whatever it is, ciphertext, whatever it is that the system is outputting. And these are random, so you need a form of average case hardness. It's not enough that some problem has some hard instances. It needs to be the case that almost all random choice of instances are hard. And what one can prove, starting with the work of Itai about 2 decades ago, is that you can prove average case hardness assuming only worst case hardness of related problems. So I'll say more about this in a few moments. And then even more exciting to at least the theoretical community is that lattices have given us solutions to what are known as like holy grail problems in cryptography, such as fully homomorphic encryption is probably the most well-known of these problems. And so this was a problem that was open for about 30 years in cryptography, and basically all solutions that have are based somehow on lattices to date. Okay, so this is why it's an exciting area. We have a lot to like, both in terms of practical and theoretical aspects of the field. By the way, please feel free to interrupt with questions. I have not enough time, or rather, I have not enough space to fill up the time. So, if there's anything unclear, you like elaboration, please do interrupt. Okay, so that's the big idea behind the field. Oh, I'm skipping around here. Okay, so what is a lattice? Informally, it's a periodic grid of points in Euclidean space. And for the purposes of this talk, I'll only be interested in integer lattices. So these are a grid of points in the m-dimensional integers. Formally, we'll only be concerned with full rank additive subgroups of z to the m. So this is a picture of a lattice in 2 dimensions. If I had more dimensions, I would show them to you, but I don't. But you should actually picture in your mind, for cryptographic purposes, lattices are usually in the several hundreds or even low thousands of dimensions. So just picture that. Okay, so a lattice can be, it's an infinite object. It goes off in all directions infinitely, but it can be represented compactly, finitely, by what's called a basis. And a basis is a set of, in this case, m linearly independent vectors, integer vectors, b1 and b2 here. And the lattice is simply generated as the set of all integer linear combinations of b1 and b2. So this point up here is 2 times b1. This point up here is 2b1 plus b2. This point over here, I think, is b2, b1 minus b2 to get down there, and so forth. And of course, we always have the origin. Now, a very important fact about lattices is that the basis is not unique. And here's another basis of the same lattice. These vectors, as opposed to these new basis vectors are somehow longer, more skew, less orthogonal to each other. And with more room, I could show you a basis which goes far, far off into the next county, but still of the same lattice here.
Okay. So,
yes.
Question. So
yes.
These basis vectors all have integer?
Indeed. Yes. So in the case today, everything will be integer. So yes, all these vectors will have integer coordinates. That's right. There are other representations, other ways you can specify a lattice other than a basis, and we'll see one in a few minutes. Okay, so lattices appear to come with many kinds of problems which we think are computationally hard for both classical and quantum algorithms. There's a wide class of kinds of problems that are hard. For cryptography, we mainly focus on a couple, which are to either find or detect the presence of so-called short non-zero vectors in the lattice. So these problems are known as SVP for shortest vector problem. Gap SVP is the decision problem of deciding or detecting whether there is a vector that's unusually short in the lattice. And then there's the short independent vectors problem, which is to find many linearly independent short vectors in the lattice. Now, the gamma subscript here denotes an approximation factor. So for cryptography, there are approximation factors associated with these problems. And that is basically to say, so that the SVP, the shortest vector problem with factor gamma, asks you to find a non-zero vector in the lattice whose length is within a gamma factor of the shortest possible. So you don't necessarily have to find the shortest vector, but one which is within a gamma factor of that. And the gamma is usually a function of the dimension, a small, like a n factor. Sorry, I'm using dimension m, so maybe an m factor, an m squared factor are the kinds of approximation factors that we deal with.
Length is Euclidean?
Yes. Sorry?
Length is Euclidean?
Yes, length is Euclidean norm, thank you. Yes. Although one could consider other L1 norm, L infinity norm. These are all fair game as well. But today I'll just be using Euclidean norm. Yes. Okay. Any questions about these? So for the state of affairs for these problems, typically the gammas that we're interested in are polynomials, small polynomials or not too large polynomials in the dimension m. And solving these problems, according to our best algorithms so far, requires at least exponential time in the dimension. And actually, if you want to get a purely exponential time algorithm, you also need to use exponential space, which in some cases is not particularly realistic. Space is often much harder to accumulate and use than time. So there are also algorithms which require smaller space, but they take something like 2 to the m log m time, or m to the m time, which is quite a bit worse than this asymptotically. So as far as we know, these problems are hard. One can get small advantages if one uses a quantum algorithm, but these asymptotics remain the same. So any questions to this point? So these are the problems that we typically rely on for cryptography. Okay, so now let me introduce to you a different kind of hard problem, which on face will appear not to have anything to do with lattices, but we'll see a connection very shortly. So the problem is known as short integer solution. It was introduced by Itai in '96, although really, when you see it, you will think this is somehow related to subset sum or various problems of that form. Okay, so for notation, we'll have two parameters, a dimension n and a modulus q. And z sub q to the n denotes the additive group of n-dimensional vectors, integer vectors, with mod q arithmetic. Okay, so you just add vectors, but you reduce every coordinate modulo q. Think of q as a small polynomial in n, so not very large. The problem is as follows. An instance of the problem is a collection of uniformly random vectors, a1, a2, up through am, which are all these in ZQN. Okay, so these are all vectors in n-dimensional vectors, mod q. And the goal, the goal of the attacker or of the algorithm is to simply find a non-trivial small integer combination of these vectors which sums to 0. Okay? So in particular, find some non-trivial z1 through zm, which are ternary and not all 0. So they could be 0 plus or minus 1, such that this sum gives you the all zeros vector. No, I'll note that without the ternary condition here, so if I allowed arbitrary values of z1 through zm, this would be a very easy problem. You could just set z1 to equal q and all the others to be 0, or you could do something more sophisticated like Gaussian elimination to solve this. And to make that clear, we can just rewrite this in matrix form. So I haven't changed the problem, I just collected things together into matrices and vectors. So all those columns, a1 through am, I just simply put into a matrix. This is an n by m matrix. It's uniformly random. And then I'm asking you for a non-zero ternary vector z such that az equals 0. So if you think you could solve this problem, please tell me after the talk, because we think it's hard. It seems to be a very difficult problem. Although it's a very natural linear algebra problem, the only tricky spot is this constraint that the z's be ternary. Okay, so if we assume for the moment, if you'll believe me that this problem is hard, then what we can do with it is build what's known as a collision-resistant hash function. This is a cryptographic object which has a lot of different applications. It's kind of a Swiss Army knife of cryptography. But here's how we can build such an object from this hard problem. So what I'll do is set the parameter m, the number of columns, to be larger than n times the base 2 log of q. Oh, yes.
How do you know the solution exists?
Very good. Yes. How do I know the solution exists? What I'm about to do will demonstrate the solution exists. Indeed. So you have to set the parameters appropriately, and in particular, doing this will guarantee us a solution exists. Thank you. Very good question. Yeah. Okay. So we'll set the parameters in this way, and we'll define the function f sub a. This is a shrinking function. So what I mean by a shrinking function is that the domain, which will be all bit strings, or 0, 1 to the m, this domain is larger than the range. Okay, so the domain has size 2 to the m, which is strictly greater than q to the n. That's the range size. Okay? So in particular, this function has collisions. It's a pigeonhole principal argument. There are some inputs which map to the same output. And the larger you set m, the more collisions that there are. We'll define this function to be the simplest thing possible. F sub a on an input x, binary input x, is simply a times x. And again, all the arithmetic is mod q. Okay, so that's my function, just a matrix times a vector. Now the maybe surprising or nice fact about this function is that it's collision resistant. That is, if I give you this function for a random choice of a, uniformly random a, it will be hard for you to find two valid inputs that hash to the same output. Okay? Or that is, if you're capable of doing that, you have actually solved the hard problem up here, I claim. Let's see why that's the case. It's actually a very simple observation. So if one finds a collision that is two distinct x and x prime, such in this binary domain, such that ax equals ax prime, well, what do? You simply subtract x from x prime, and that gives you a solution. So this vector z is now, because x and x prime are binary, this vector z is now ternary. So all its entries are 0 plus minus 1. Because x and x prime are distinct, z is non-zero, and indeed a times z equals 0 just by simple arithmetic. Okay, so we've solved, by finding a collision, we've implicitly solved this SIS problem. So any questions about this? It's kind of, you're saying, come on, like do something interesting here, do something non-trivial. So we'll do that right now. So, okay. Okay, so that's all very nice, but what does this have to do with lattices? It turns out a lot. So the first observation is that there's actually a lattice hidden in this SIS problem in the following way. If you consider this uniformly random matrix A from the previous slide, what one can do is define what's been called a Q-ary lattice, which is the lattice of all vectors z such that az equals 0. And here I'm not considering any restriction like it has to be ternary or anything like that. So all integer vectors z are fair game. They should just satisfy az equals 0. And so this is often called the perp lattice, or L-perp of A, treating A essentially as a parity check matrix, or arity check matrix in this case. So we get a lattice that looks something like this, and it's Q-ary because, well, the vectors Q times every standard basis vector is in the lattice. So the lattice is basically formed of shifts of this box here, and you just shift it by Q in any direction that satisfies that. The solutions that we were interested in, these ternary solutions, or if you relax the ternary constraint a little bit, lie in this ball of relatively small radius here. So these are the short integer solutions to az equals 0. And all the others are too long for us to consider them good enough. Okay, so this is the lattice connection to it, or a lattice connection. And in fact, there's a much stronger connection to this, which is what's known as a worst case to average case reduction. Originally shown by Aitai in '96, it's been improved in many, many works since then. But they all have the following flavor, which says the following. If you are capable, if your attacker is capable of finding a short solution, so finding some kind of short non-zero vector z in this lattice for a uniformly random matrix A. Okay, so the game is we choose a uniformly random A and ask the attacker to find a short vector. And by short, I mean its Euclidean norm is less than beta, where beta is much smaller than q, of course. We have trivial solutions of length q, but if one can do a lot better than that and get a length beta, then any such algorithm, any such method for doing that can be converted into an algorithm that solves these hard lattice problems, gap SVP or SIVP, to within approximation factors roughly beta times square root n. Okay, and that holds for any n-dimensional lattice. Okay. So this is a transformation. If you can solve this problem on random lattices from this family, then you can actually solve these hard problems on any lattice of the corresponding dimension n. And this is a very powerful statement because a priori it's not clear how you should choose random lattices. You know, if you're going to do cryptography, it's not clear what distributions you should use, how you should generate your lattices. This theorem tells you this is a safe way to do it. If you can break these, you can break all lattices of a corresponding dimension. So this is a very, very nice work, really breakthrough seminal work that's been built upon the whole theoretical edifice of lattice cryptography. In some sense, is built upon this. So any questions about this theorem here? Okay. So let me show you another application. I showed you the collision-resistant hash function, which by itself is useful. But in fact, there's many more interesting and powerful things we can do with this SIS problem. And one example is digital signatures. So the idea behind a digital signature is that let's say I'm the signer, I can create a public and secret key pair. And I can publish the public key to the world. And then when I later want to sign or attest to some messages, like my last will and testament, I write out my will, giving all my money to the Carnegie Institute. And not that they need it, but it's a very nice building, you have to admit. So I write my will and testament, and then I attest to it. I use some signing algorithm using my secret key combined with this message, and I release what's known as a signature. And then anyone knowing my public key, the signature, and the message can validate that, yes, this came from Chris. And so it should be easy for me to produce signatures using my secret key, but hard for any outsider to forge a signature that is convincing to the judge. Okay. So this is what we're going for. And here's kind of a template of how one can do it. So what we'll do is generate, as our key generation procedure, a verification key or public key, which is simply a uniformly random matrix A, as in the previous slides. But then along with this, we're going to generate what's known as a trapdoor. So the secret key will be some kind of trapdoor T for this matrix A. And I won't tell you exactly what the form of this trapdoor is, but you can think of it as somehow a set of very short vectors inside this special lattice A. Okay, so we have algorithms that can do this. You can think of it as akin to generating an RSA modulus together with its two secret factors, prime factors, right? Some kind of connection with this. So instead of the factorization being the trapdoor, we have a set of very short vectors acting as a trapdoor. So we can generate these two in concert together. And then for me to sign a message, so I write my last will, and together with the secret key, the trapdoor, what I will do is use the trapdoor to randomly sample a short vector z satisfying az equals some kind of magic hash of the message. So what I would do is apply some kind of magic hash function to the message. This will give me a vector in ZQN, and then I will simply solve for az equals that right-hand side. But I'm going to solve it in a kind of funny or sophisticated way. It's not enough to just find a short solution. I'm going to randomly sample from among the many, many possible short solutions z. Okay? And in particular, the way I'll do that is I'll draw z from, what I'll need to do is draw z from a distribution that essentially reveals nothing about my trapdoor T. And in the work with Gentry and Vaikuntanathan, we proposed that you use a so-called discrete Gaussian distribution over the solution set. Okay? So this is a Gaussian, but it's limited exactly to those valid z's that satisfy this condition here. Okay? And we have algorithms which actually sample with high fidelity from this kind of distribution. Okay. So the important point, though, is that the way that you draw the signature z should not reveal anything about the underlying trapdoor that you're using. And that's been a sticky point with earlier proposals for signatures, which have ended up being broken or weakened because they leak some kind of information. Okay. So to verify a signature, the judge, it should be relatively clear what the judge should do. The judge is given the public key A, message mu, and a purported signature Z, and simply checks that A times Z is indeed the magic hash of the message, and also that Z is a sufficiently short in Euclidean form. So it's clear that if one signs in this way, verification will check out if you set up the parameters appropriately. What's less clear is why should this be secure? So why should it be hard for a forger to produce good signatures, maybe even after it has seen other good signatures on other messages? So the argument, and I won't be able to give anything close to a real proof, but the security argument here is that if one attacker wanted to forge a signature on a new message, say mu star, then it would have to find, by definition of what's required for verification, it would have to find some short Z star such that AZ star equals the hash of mu star. Now, this hash of mu star, by assumption, is going to be just a truly random vector, ZQN, and so therefore one must solve AZ star equals some random right-hand side. And this is exactly the SIS problem that we showed before. Well, it's an inhomogeneous version of it, so it's IS-IS. This is IS-IS. Okay, so that's a hard problem. Okay, yes?
But forging this signature does not require the forger to find a random star. Any of the star will do.
Indeed, yes. So
He has to find a random one.
right, so very good point. The forger gets its choice of message that it wants to forge on. Essentially, as I've said, this hash function is somehow magic. It's modeled as a random oracle, which is kind of a standard heuristic for RSA signatures and other kinds of signatures as well. So you assume that the hash function is crazy enough or magical enough, and this is a heuristic assumption, that even one's choice of mu star doesn't give you any control over what the hash function does to it.
That wasn't my question.
Oh, it wasn't your question. Okay.
It's a good answer to a
Different question. Great. Okay, let me give you a different good answer to a different
My
question.
was about, you said that the forger has to find a random star.
A random mu star?
Z.
Oh, Z star. No. The word random does not appear in this.
You said it.
Okay, I didn't mean to say it if I did say it, but indeed, all the forger needs to do is find some sufficiently short Z star. Yeah, and that's okay. But this is the SIS problem. It's just to find any valid, short enough Z star satisfying this equation. Right. So the contrast here is the legitimate signer, to protect itself, should be sampling from a nice distribution that doesn't leak. A forger is not obligated to do anything, it just needs to find something short enough. Okay, but that problem by itself is hard.
Even if you've seen several previous ones.
Yes, exactly. So there's an argument to be made, but having seen previous signatures, one needs to argue that because they're coming from this distribution, they don't leak anything useful. Yes. Yeah. So there's definitely a proof to be given here, which I'm not giving right now. Okay, great questions. Any other questions with this?
So
Yes.
in the picture, you show how Z is chosen.
Yes.
But how does it relate to the secret key?
Yes, so the secret key, right, I'm hiding a lot of details. The form of the trapdoor, you can think of it as a bunch of relatively short vectors in the lattice specified by A. And then what one wants to do is use these vectors and somehow take random combinations of them in a way that produces this nice clean distribution here. Okay? And there's a way to do it. It's technical, but it can be done. Okay. Yes?
Just to clarify, so is that hash function here the same as the shrinking function?
Very good question. No, absolutely not. Do not do that. So the question is the hash function here the same as the shrinking hash function I showed a few slides ago? No. So you should not, I don't know for sure if there's an attack. There probably will be, or it seems very dangerous. So what you want is for this hash function to be acting somehow like a random oracle, which is a magical object that cryptographers invent to make things efficient. Okay? But it's a standard heuristic that, yeah, billions of gallons of ink have been spilled over this technique, but there we have it, yes. Yes? Good question. So does an honest signer need to generate a new A to produce new signatures? No. She simply generates a new Z. So for each new message that you want to sign, you get a different hash value, and you simply solve, you need to solve for a new Z or sample a new Z relative to the same A as before. The security depends on finding, well, this A is the public key, it's fixed for all time, and in order to forge, one has to solve this equation for some random right-hand side. So the A is random, the right-hand side is random, and the forger has to find such a Z. Yes?
Yeah, so to clarify, the reason it's hard for forgers is because they do not have a secret trapdoor.
Well, if the forger did have the secret trapdoor, it would be very easy to forge. Yeah, so you could just do what the legitimate signer does, right? So there's some kind of, I don't want to say that it's only hard because he doesn't have the trapdoor. It's hard to forge because it's hard to solve the SIS problem. Okay, so this is kind of the flavor of the, and the ideas behind this digital signature scheme here. Okay, let me shift gears now a little bit. We can do many interesting things with the SIS problem, but we can do many, many more interesting things with another hard problem, which I'll now introduce. It's called learning with errors. It was introduced in 2005 by Oded Regev. Although it inherits from problems in coding theory, learning parity with noise. If you've heard of any of these problems, it's quite similar. So this problem has parameters n and q, just like SIS did, but it also has the error distribution. So once you fix n and q and some error distribution, you have a learning with errors problem. So this is really a family of problems. And the problem is as follows. So there's a search version, which is as follows. We choose a secret vector S. Again, it's an n-dimensional vector mod q. And the goal of the search problem is to find the secret S given many noisy random inner products with S. So what I mean by this is that the attacker is given many samples, as many as it wants, really, where each sample is generated by picking a random AI, n-dimensional vector, and then giving the attacker the inner product of S with AI, but with a little bit of noise added in. And the noise that's added comes from the error distribution. Okay, so to make it a little more concrete, the BI is just S inner product AI plus an independent error term drawn from a distribution. And the distribution that Regev contemplates and is often used is a Gaussian type distribution, but restricted maybe to the integers. Or it could be continuous. It doesn't matter too much. So these error, just to give you an idea, the size of the error, the standard deviation is roughly square root n or more, which we would like to be much smaller than q. And it has some kind of rate. So once you've set the width of the error relative to q, you get a rate alpha. So alpha is basically the width of the error divided by q. It's kind of the relative amount of error that are in these equations. A's and B's are both given to the attacker, and the attacker's goal is to find the secret S. Okay, we can rewrite this a little more compactly with matrices and vectors as follows. So the matrix A is exactly as I did before. All the AIs are just the columns of A. And now, essentially, we're multiplying on the left. So we have the secret multiplied on the left by A, taking a random row combination, adding in an error vector where each entry comes from the error distribution, and everything is mod Q. So we're given A and B, which is approximately S times A with errors added.
Or just T is transpose.
The T is transpose, yeah. This upper, right. So all my vectors are columns. S transpose is a row vector. Yeah. And likewise, E and BT are row vectors. Okay, so before I was multiplying on the left, A times Z equals something. Now I'm multiplying on the, before I was multiplying on the right, A times Z equals something. Now I'm multiplying on the left as just a convention. Okay, so that was the search problem. The decision problem is slightly different. It's to distinguish pairs AB generated in this way from just truly random uniform A-B pairs.
So
Yes.
solving this system of noisy linear equations is a different problem? Like if I corrupted a constant fraction of the
Yes.
equations, that's a different hardness assumption?
It would be, yeah, so the question is solving a system of noisy linear equations, where say you corrupt 10% of the equations, and how are you corrupting them? Maybe you're sending them to a random, uniformly random right hand. Yeah, so that qualitatively somehow appears to be qualitatively similar. No, I don't think any relation is known, right? So you're contemplating either 10% are just completely wrong and the others are completely right. This picture, everything is a little bit wrong. Yeah. Well, almost everything is a little bit wrong. Yeah. So, yes.
It's the difference.
Right.
But I don't see why we talk about learning instead of solving integration.
Yeah. So it's mainly just a vocabulary thing. So there's a problem called learning parities with noise, which goes back probably to the 60s or even earlier, which syntactically is almost exactly this. So for historical reasons, the learning theory community concerned with learning, these are the kinds of problems they often contemplate. Yeah. Yeah, it has to do with everything. Learning theory, coding theory, lattices, everything, yeah. So you can give this a lot of names, but this is the one that the inventor chose. Okay. So again, the decision is seemingly maybe an easier problem. It's simply tell whether you were given this kind of AB or this kind of AB, and do so with some advantage over random guessing. So we have some remarkable theorems. Just like with SIS, we have worst case hardness for this LWE problem. So it's a chain of reductions, which looks something like this. So solving the search LWE problem is at least as hard as solving approximate lattice problems in the worst case with factors roughly n over alpha. Okay, so this alpha, remember, is the error rate. And so as the error rate decreases, as it tends to 0, these approximation factor will go up, and you'll have a potentially easier problem here. But you have a nice smooth trade-off between the error rate and the approximation factor. And what's really interesting, so Regev showed this theorem here, which is a quantum reduction. So it says that if you can solve search LWE, maybe by classical means or by quantum means, doesn't matter, what you get out of it is a quantum algorithm for these problems. And so this reduction is somehow inherently quantum, whether or not the original solver here is classical or quantum. And then one can go from search to decision. So this decision problem actually is essentially just as hard as the search problem via a classical reduction, which goes back to Blum et al. Actually, they attribute it to the folklore. So this is something that's been out in the world for a long time. But this polynomial equivalence of search and decision is a relatively straightforward argument. And then, assuming that decision is hard, one can build a variety of crypto systems encryption type schemes. I'll mention there are also some fully classical reductions which eliminate this quantum aspect of the reduction. But one has to take worse parameters or maybe non-standard problems on the left-hand side here. But that's an alternative additional evidence we have for the hardness of LWE. Okay, so from this point, what we'll do is talk about what can we do with decision LWE, although it's a very important problem to understand the quantum complexity or whether these problems are actually hard for quantum, since it underlies the whole chain of reductions here. Okay, so we can do a lot with LWE, a lot of crypto. So we can do all the kind of basic workhorse things that one expects to do with RSA, elliptic curves, things like that. So you can do key exchange, public key encryption. These are equivalent, essentially. You can do oblivious transfer, which is the core piece of multi-party computation protocols. You can do actively secure encryption without these random oracle heuristics. You can even do exciting things like block ciphers and pseudorandom functions. You could do much more advanced things like identity-based encryption with and without random oracle heuristic. And then things get really crazy. You can solve wide open holy grail problems like fully homomorphic encryption, related problem called attribute-based encryption, and the list just goes on and on and on. So going from practice, from sort of practical workhorse things down to really crazy out there stuff. And LWE is behind all of these. Yes? So let me just show you the easiest thing one can do with LWE. It's a Diffie-Hellman-like key exchange, which is more or less implicit in the very first works and has been optimized in many ways since then. So it works as follows. We have Alice over here on the left and Bob on the right, and what they would like to do is communicate over a public channel to establish a secret key known only to them. Okay, so that an eavesdropper won't be able to learn about the key. So it works as follows. As before, we have a matrix A. It's going to be, in this case, a square matrix, n by n. And either party can choose it, or it can be chosen by a trusted third party who you trust to choose it randomly without a trapdoor in it, which maybe that makes you uncomfortable. So one of the parties maybe should choose this matrix A. But then to actually run the protocol, here's what they do. Alice will choose a vector R, an n-dimensional vector R, from the error distribution, and Bob will do the same. We'll call his vector S. And then they engage in a Diffie-Hellman-like procedure. So, but it's going to be slightly different. So Alice will send over R times A, R transpose times A, so she multiplies on the left and adds some error and sends over the vector U that results. Bob does the same thing symmetrically, but on the right-hand side. So he multiplies A times S, adds some error, and calls that V and sends that to Alice. Right, and now Scott will tell you what happens next. So in order to establish their key, Alice will multiply her secret R times Bob's public message V. And notice that up to the error terms, this is basically R times A times S. Okay? So what you get is R times the error that was inserted here, but because R and the error terms are all small, it doesn't add up to much. Okay, so this R times V is approximately RAS, and symmetrically for Bob, he takes Alice's U vector, which is approximately R times A, multiplies it by his secret S, and gets something which is approximately R times A times S. Okay, and so we'll call that that vector K. Maybe add a little bit of error here to get the key K. Right, so what we have in the end is that both Alice and Bob have something which is approximately R times A times S. And because there's some error, they have to resolve this in some way. There are a variety of ways you can do that. For example, they can just both use the most significant bit of their respective values of K. And that's likely to be equal on both sides. So they throw away the low order information where the errors are and just take the high bit, for example. You could do more sophisticated things. In any case, what we can show is that an eavesdropper who is passively listening to these messages and sees everything, so it sees Alice and Bob's messages UV, and then a purported value K, or the true value K, cannot distinguish this world from a world where everything is just truly random garbage. So here's how the argument goes. It's rather simple. So consider this is the real world of what the eavesdropper sees. But by decision LWE, this vector U is just a noisy R times A, and so it's pseudo-random. So this U and A can be switched out to uniformly random A and U. And this holds by the assumption that decision LWE is hard. K is the key that they both, K is the key that Bob gets. Yeah. Okay, so that's one switch. This world here, the real world, is indistinguishable. Yes. Okay.
That the eavesdropper gets to see the key.
Right, so this is a standard modeling of key exchange. One wants to show that all the public information together with the true key is indistinguishable from the public information and a random key that's unrelated to it. Right, and that's the way one models security for key exchange. Right. Yeah, it's a little strange to say, oh, we're giving the attacker the key. But what we want to show is that the true key is indistinguishable from a truly random key. Okay. So the first step is we've switched this A and this this noisy product U with a truly random U. We could do that by decision LWE. And then we're just going to repeat the argument on the other side. So here V is just A times S with noise, and K is U times S with noise. But both A and U in this case are truly uniformly random. So that allows us to switch both V and K to be truly random as well, again by the same decision assumption, decisional LWE assumption. And so by this kind of game hopping or changing the worlds in indistinguishable ways argument, we show that the real view of the attacker is indistinguishable from a world where just everything is random junk. Okay. Yes?
Just to be sure I understand your notation, as into blue in random.
Yeah, red is somehow the structured LWE vectors, and blue is just random stuff. Whoops. Oh. Okay. Yeah, so I'll leave this here. This is Diffie-Hellman, but using associativity of matrix vector multiplication instead of commutativity in the exponent. And dealing with the noise properly. Okay, so we'll now switch over to a line of work that aims to get much higher efficiency using what's called rings, ring structure, polynomial rings. So both SIS and LWE, as I've said, look rather efficient. They're just vectors and matrices being multiplied together. And this is rather efficient, but maybe not quite efficient enough in some ways. So, for example, in LWE, if you want to get one pseudorandom scalar, so these BIs, which are just A inner product S plus an error term, this requires doing one n-dimensional inner product mod Q. So that's pretty cheap, and you can do further things. You can, for example, use the same A's over many different secrets S, but you're still always left with doing a linear amount of work to get one pseudorandom scalar integer mod Q. Okay. So it doesn't sound terrible, but we'd like to do better. And another inherent problem, which is perhaps more serious, is that this means that the crypto systems have to have rather large keys. So in all the applications I've shown you, this matrix A, whether it's tall or fat, it always has at least n rows or columns and at least omega n or even more in the other dimension. And so the size of the key is at least n squared and then some log q squared as well. And so that can be quite large when n has to be in the many hundreds or even near 1,000. So the large keys could be problematic. So anyway, inherently we have these n squared size keys and n squared running times to encrypt and decrypt. What we'd like to do is improve upon that. So some wishful thinking, if you were to look at LWE, would be to say, look, instead of doing inner product, A and S, what if we could define some magical operation star that maps two vectors into another vector? So AI star S, and then add, that gives you a vector, you add in a noise vector, and you get a whole vector of BIs. And so, could we hope to get n pseudorandom scalars in this right-hand side from just one cheap star operation here? Okay, and furthermore, in terms of the keys, what this would allow us to do is replace each square chunk of the key, n by n chunk of the A matrix, with just a single vector, n-dimensional vector. Okay, so it gives us both improvements in space and time. So the main question here is, well, how to properly define this star product so that you actually have any security at all. Okay, and you'd like these A-B vector pairs to be pseudorandom. And you have to be extremely careful with this. Naive choices like just doing a coordinate-wise multiplication are completely insecure. You can break it very easily. So that exercise to take home. Okay, so the answer, a better answer that works, is to define the star operation as multiplication in some kind of polynomial ring or other form of ring. A commonly used example is ZQ adjoin X. So this is polynomials with integer mod Q coefficients, always reduced mod X to the n plus 1. something like this. Okay, and you can do, what's nice about this kind of ring, or related ones, is that you can do multiplication in these rings very fast using fast Fourier transform type techniques. So about n log n operations, quasi-linear number of operations to do this star operation here. So this idea actually goes back quite a ways. In fact, to the first, one of the first lattice-based encryption proposals called ntrue was based on these kinds of ring structures. And then it was added to this idea was used in the theoretical literature, first by Michancio in 2002, and in works since then. So using this ring structure for efficiency is an idea that goes back almost 2 decades and is getting a lot of attention now because of the efficiency properties. So let me describe to you learning with errors over rings. So we call it ring LWE or LWE over rings. And this is a highly oversimplified version of the problem, but it should give you a flavor of how it looks. So we're going to define the polynomial ring, integer polynomials, mod x to the n plus 1. So anytime the degree, you have a monomial of degree n or more, it wraps back around. So x to the n becomes -1, x to the n plus 1 becomes -x, and so forth. And for technical reasons, n will be a power of 2 here. And then r sub q will just be this ring with mod q coefficients. Okay, so all coefficients are reduced mod q as well. Okay, so as I said, an element of RQ is just a polynomial of degree less than n, and it has mod q coefficients, and one can do operations very quickly in this ring using FFTs. Okay, so the search version of ring LWE is very much like with plain LWE, just some small tweaks. Instead of doing inner products, we do ring products. So we have a secret element of the ring denoted S, so you can think of it as a polynomial. And you're given noisy ring products. So you're given a random A, and then S times A plus some error. And here the errors are also polynomials. So each error term is itself an element of the ring, and these are somehow small. So the coefficients of the error are Gaussian and small, but not too small. Okay, and one's just given a lot of noisy samples and is asked to find the secret ring element. The decision problem is analogous. One wants to distinguish noisy ring products from just truly uniform pairs of ring elements, AI, BI. Okay. So any questions about this here? Again, the takeaway point here is that the product here is no longer an inner product, so it maps a ring element S, a ring element A, to another ring element, not just a scalar. And then you add a noise term also, which is a ring element. Okay, so we can prove some things about ring LWE. 2 main theorems that we have so far, or reductions. So this says the following, similar in spirit to what we had for plain LWE. The search version is at least as hard via a quantum polynomial time algorithm. It's at least as hard as approximate shortest vector problem, in the worst case, on what are called ideal lattices of the ring. So these ideal lattices have correspond to ideals in the ring R. They have additional algebraic structure, but one can define, the shortest vector problem, approximate shortest vector problem on such ideals, and we proved that solving search is at least as hard as solving these problems with a quantum polynomial time algorithm. Yes?
Is it potentially easier to solve on ideal lattices?
Yes, absolutely. So this is a restricted class of lattices. They have algebraic structure. I'll define what they are in a moment, but they're certainly not general lattices. So they're not arbitrary. They have to have this algebraic structure to them. So potentially easier. As far as we know, for the kinds of parameters that we use here, we don't have any improvements that use that algebraic structure, but we can't rule it out either. Okay, and then separately, there's a search to decision reduction. This reduction is classical, and it works currently for any what are known as cyclotomic rings. or more generally Galois rings, of which the example I've shown you is one particular case. Oh, I should mention, this part of the theorem actually does not require cyclotomics or Galois or anything. It works in any ring of integers of a number field. So if you don't know what any of these algebraic things are, don't worry about it, but that's the flavor of the result. Okay, so here I'm just saying in words what these symbols mean, and then we do this. Okay, so this is ring LWE. I'd like to spend, since there's a little bit of time, I'd like to spend just a few moments on what are ideal lattices, just to give you an idea. So again, we fixed our ring here, Zx mod x to the n plus 1. An ideal is a subset of the ring, which is an additive subgroup, so you can add and subtract and you remain inside the ideal. But in addition, you can multiply any element of the ideal by any ring element and you remain inside the ideal. Okay. So for the ring of plain integers, the even integers are an ideal, because if you take any even number times an integer, you still have an even number. But with polynomial rings, there's much more interesting things going on. So to get ideal lattices, what we'll do, an ideal lattice is simply any ideal of the ring treated as a lattice. Okay, so how do we treat it as a lattice? Well, the most obvious answer, which will suffice for this talk, is what's known as the coefficient embedding. So you have a polynomial a0 plus a1x plus an minus 1x to the n minus 1. It can always be written in this form because of the way we're modding here. And you simply write out its coefficient vector. And that's a vector of integers, and that is a point in your lattice. So for the rings we're talking about today, this is really all you need to know. And I'm going to skip there's an alternative way you can do it, which not particularly important for today. But I'll let you take a picture of it if you want to. Okay, so here's a pictorial version. We have a two-dimensional ring here because we're modding by x squared plus 1. And it looks something like this. So it's this sort of the rotated integer lattice in this case. And then here's one ideal I, which is generated by the polynomial x minus 2 and 1 minus 3x. So this you can prove with a little exercise is an ideal in the ring. And so all the elements of that ideal are denoted here in red. So the red points form an ideal. Okay? And so these red points form a sub-ideal of the ring, but every ideal gives you a different sub-lattice of this ring here.
Automatically a lattice.
Yes?
It's automatically a lattice.
Automatically a lattice, that's right.
Because of the ideal.
Yeah, well, it's automatically a lattice because it's discrete and because it's a additive subgroup. So the additive subgroup part automatically makes it a lattice. The fact that it's an ideal means that it has these symmetries or closure properties, which in general you would not have in a lattice. Right. So the shortest vector problem, or the approximate shortest vector problem on ideal lattices, well, if you give me some arbitrary ideal I, represented as a basis, for example, then the goal is to find a nearly shortest non-zero vector in that ideal. So this is the problem that underlies the reductions that I showed you on the previous slide. Okay, so indeed, it's already been asked, what about the complexity? Are these ideal lattice problems hard or not? And this is a big open question still, is to determine how hard or if they are hard at all. And also to understand the relationship between these problems and the ring LWE problem. So for example, we have this quantum reduction which says that approximate SVP is a lower bound on ring LWE. But actually we don't know about the other direction. So we don't know if this goes in the other way. Or said another way, if you had an oracle that could solve approximate SVP on the ring, on ideals, then could you use it to solve ring LWE? This currently is unknown. I would like to know whether the answer is positive or negative, but we don't really have an answer to that. And the reason essentially is that ring LWE samples don't seem to translate to ideals in the ring. They translate somehow to modules over the ring, but it's hard to get ideals out of them. So it's interesting to work on this question, I think. And then, of course, the second question is how hard or easy is this problem in the first place in cyclotomic rings or in other rings of interest? So again, it's been pointed out there's a lot of structure here. There are subfields, there's symmetries, there's Galois automorphisms, but currently we don't have any significant improvement versus general n-dimensional lattices for the kind of approximation factors that we deal with in cryptography. However, we had a recent work with Kramer, Duka, and Regev building on different parts of things that have been happening on these questions, where we were able to show that you can solve large, but perhaps non-trivially large shortest vector problems. So 2 to the square root n log n approximation to shortest vector problem in quantum polynomial time. So there's a quantum algorithm which can achieve this approximation factor for any, well, now, thanks to this work that just appeared in the past few days, this applies to any ideal in a prime power cyclotomic, and this may generalize to other rings as well. So, yes. How is it a threat to N-true? We don't know. It seems quite far from being able to apply it to N-true or to ring LWE. But, yeah, so for a couple of reasons. 2 reasons is the approximation factor is much larger than what's used for crypto. And second, because N-true and ring LWE, we don't actually know how to cast these as ideal lattices. So there's 2 kind of barriers which are preventing using this result in any kind of cryptanalytic fashion. But who knows what may come of it in the future. So that's a kind of active area of research right now, and those who know quantum may be able to contribute. And then also mention there's actually a 2 to the root n over log n barrier for the main technique used in all of these works. So one would have to overcome this kind of inherent barrier here, but maybe there are ideas that could do so. Okay, so for the remaining time, I'd like to switch gears very completely. So we've been talking about math and theoretical foundations for all this time. I'd like to talk a little bit about practical implementations that have been coming out of research labs and other groups. So for the key exchange, this Diffie-Hellman-like protocol that I showed you a few slides ago, when adapted to the ring LWE type setting, so there's an easy adaptation to ring LWE. In 2015, there was a proposal called New Hope, okay, allusion to Star Wars there, where they gave a version, an implementation of a ring LWE key exchange with many optimizations, a lot of clever ideas, and an analysis, a cryptanalytic analysis, which led them to conjecture at least 200 bits of quantum security. So with quite a comfortable security margin, according to our current knowledge, at least. And they implemented it. They gave optimized implementations in both C and using AVX2 instruction sets on Intel processors.
Sorry again.
Yes.
Just to be sure.
Yeah.
Of course, you don't mean that to break it, it's not going to 2,000 quantum bits. What you mean is we take 2,000.
Oh, yes, sorry, yeah. So thank you. Yeah, very, very good point. To break it does not require 200 bits. Okay, so to break it requires 2 to the 200 steps of computation on a quantum computer. Thank you for making me clarify that. Yes, yeah. Being secure against a 200-bit quantum computer is not interesting, I think. Okay, so they conjecture 2 to the 200 work would be required to break this, according to their analysis. And what they showed is that in efficiency, this is actually comparable to, or in some respects even faster than, highly optimized state-of-the-art elliptic curve Diffie-Hellman that has 128-bit but non-quantum security because it's based on the Diffie-Hellman protocol. And we learned a couple months ago, I think, over the summer, that Google has actually now deployed this in, a hybrid New Hope plus elliptic curve Diffie-Hellman in Chrome Canary, so it's the bleeding edge experimental version of Chrome, and on its own web servers, and in the boring SSL library that's out there. So this is actually being used in practice. You can download, Chrome Canary and use it, and people have taken screenshots of their New Hope established SSL connections or TLS connections. So that's exciting that this stuff is actually working in practice and appears to be quite efficient. I should point out that this conjectured security is coming from the cryptanalytic side. So what they're looking at is the best attacks that are known against the parameterizations that they used. They're not relying on the theorems that I've been showing you throughout the day. And so many of the optimizations are kind of cutting corners or optimizing away what the theorems require. So it's an important question to understand, what do these concrete parameters actually do? Or what kind of security do they have? And does it matter that you stick with what the theorems ask for, or do you kind of optimize things down a little bit? Okay, so then there's a follow-up work by many of the same authors and many additional called Frodo, continuing on the sci-fi fantasy theme here. And it's called Frodo because it removes the ring. Okay, I know. Okay, so it's called Frodo. Take off the ring. So they remove the ring structure and kind of go back. They go to a little retro, and they go back to plain LWE, and they do the plain LWE key exchange. Again, with many optimizations and cool tricks. And their parameters, they conjecture, offer 128 bits of security against quantum attacks. So it's been believed that, kind of the reason we had ring LWE in the first place is that LWE wasn't efficient enough, and the keys were too big. So one of their ideas is to just kind of find a way of compressing the key down a whole lot and taking care of that, and then they have to deal with these matrix vector type multiplications. And the upshot is that they're able to do it reasonably fast. So in the end, their protocol is roughly an order of magnitude slower than New Hope. So they take some price there in efficiency, but it remains only about 2, maybe 3 times slower than comparable elliptic curve Diffie-Hellman. So maybe this is fine. Maybe this is just efficient enough, and we don't have to use ring structure to get acceptable efficiency. So this is a very exciting piece of work as well. And there also, I should mention, have been proposals to use a hybrid between plain LWE and ring LWE, sometimes called module LWE. So if you want to look that up, it kind of interpolates between the two extremes of fully plain LWE and fully ring LWE. So in the end, it may be that we end up using something in between these two to get benefits of both. Okay, and then let me mention, so since I talked about digital signatures earlier, I also mentioned there have been several proposals of practical implementations of digital signatures. And most of these don't follow the exact design that I showed you on the slide before. They follow a design that came from Lubashevsky in 2009, improved in 2012, and in subsequent years. It's very similar in qualitative spirit, but the technical details differ rather a bit. So one of the most prominent works on this is a work called BLISS, which stands for bimodal lattice something, something, something. But they came up with a good acronym for it. And this is an optimized implementation in Lubashevsky's framework. And it also offers pretty compelling efficiency. So this is a table or some numbers from their paper which compare efficiency of RSA 4096-bit keys, elliptic curve DSA with 256-bit keys, and BLISS, and all of these are conjectured to offer at least 128 bits of classical security. Of course, these are not quantum secure. So looking at the numbers here, you see some things which are better and some things which are worse for BLISS. So for example, signature size in kilobits, 4 kilobits, half a kilobit, 5.6. So a little bit bigger than RSA, but not terribly bad. Public key size also a little bit bigger by about 75%. what's more interesting is the speed of this. So you can do, this is thousands of signatures per second. RSA can do 100 signatures per second. Elliptic curve, 9,500. They get 8,000. And verification is really where it shines. 33,000 signature verifications per second, which is a factor of 5, almost 5 better than either of the previous two. So this is great, and there are probably many more optimizations that Bliss can be amenable to. So this is ongoing work, but it gives you a flavor of what these can do right now. I'll mention a couple of other implementations. So going from the kind of workhorse key exchange signatures everyday stuff to the more farther out stuff, we have HElib, homomorphic encryption library by Halevi and Shoup. This is what they call an assembly language for fully homomorphic encryption. So it offers, actually implements many very advanced features. It's sort of been a test bed for this group at IBM and others to implement a lot of the theoretical work, put it into practice, and see how it does. So this holds most speed records by virtue of the fact that no other library does what it does. So de facto, it wins. But it does give some reasonably interesting performance for fully homomorphic encryption tasks. So they've done a lot of really neat things with HElib. And then I'll just plug a work with my student, Eric Crockett, which will appear at CCS this year. So this is Lambda Composed Lambda, or LOL for short. And what we're aiming to do is give a very general purpose, high-level framework aimed at implementing the wide variety of advanced lattice crypto systems that are out there. And so we're taking a language approach to this, and we focus on a lot of modularity, safety through type systems, and being consistent with the best theoretical recommendations for these kind of systems. So you can check that out if you're interested. Okay, just down to the last couple minutes. So just to conclude, I hope I've convinced you that lattices are offering us a very attractive foundation for so-called post-quantum cryptography, both from very basic tasks to exciting advanced tasks of the future. And at the same time, for a lot of the practical purposes, the cryptanalysis and security estimates, so far, this is a subtle area. There are many more parameters that have to be balanced. We don't know, in many cases, what the best algorithms are. There's a variety of different types of algorithms which have different trade-offs. So this is a subtle area with a lot of work that's been ongoing, by far from mature, but I would say it's maturing. It's kind of in the awkward adolescent phase at this point. So we need work on this, and we especially need work to understand the quantum, conjectured quantum security of these kinds of systems. And furthermore, I think that what's really cool to me personally is that this seems to be a very nice story both for rigorous theory and also practical engineering alike. So all these systems that were built in practice really came out of good theoretical ideas, these worst-case hardness proofs, ideas about distributions that don't leak information, all these kinds of things. And these ideas were then able to translate quite well from the theoretical realm into the practical realm and have demonstrated real-world utility. So with that, I'll thank you for your attention and take any other questions.
Question.
Yeah.
When you say they have the 200-bit security, so it takes 2 to the power of 200 steps on a quantum computer, are there certain algorithms used, or how is this?
Yes, so the 200-bit quantum security means that the authors estimate it takes roughly 2 to the 200 steps on a quantum computer to break it. So this is assuming the best known quantum algorithms, the performance of the best known quantum algorithms to date for the parameters that they selected. So generally speaking, the best algorithms are some kind of form of lattice basis reduction, perhaps with sieving as subroutines or quantum sieving as subroutines in smaller dimensions. So there's a lot of analysis that has to be done to determine where's the cutoff between sieving, how small of a dimension you should use, how does it interact with the basis reduction, and so forth. And so I should mention a lot of these estimates that came out were actually, the authors think, and as far as I understand, I agree, they're taking quite conservative estimates. So they're really underestimating the amount of time it takes these algorithms to do the work they need to do, and still they're coming out with 200 bits of quantum security. So, you know, as with anything in crypto, if some radically improved algorithm comes out, you have to reapply the analysis and see what you get. At the same time, I think people are generally being quite responsible and conservative about underestimating the cost of the attacks, at least according to our knowledge. Yes? In the back there?
Yes. I want to understand the main problem with Lattice.
For understand, the main problem with lattice-based security is the size of the keys. Is that correct, or?
That has been, so the question is the main problem or the sticky point with lattices is the size of the keys. You know, as you can see from these practical implementations of signatures, for example, you know, when you move to the ring setting, or when you do things like they did in the Frodo work, they've largely managed to mitigate most of those concerns, or at least the keys are not unacceptably large. So, you know, if a 7 kilobit public key is acceptable, then we've gotten under that threshold. So, you know, key size, certainly you're not going to match the key size of elliptic curve type crypto. Those keys are extremely compact, but you're also not in the realm of, you know, unreasonably large anymore either. Yes. Yeah, let's try that one.
Yes, can you hear me? Okay. But how many quantum people are seriously trying to attack these crypto systems?
Right, how many quantum people are seriously trying to attack these crypto systems? Some, and not enough. I mean, the number of people who are experts in both quantum and lattices is, I don't know an exact number. I can count it on my two hands, and not in binary, right? I mean, probably it fits in two hands.
The world rely on this kind of securities, which could be based on just so few people looking at the problem.
Yeah, it's a fair question. How, you know, how much scrutiny of quantum, you know, do we really understand? I'll say that my point of view, and I think this is pretty much a consensus, is that if you want to, we need to deploy post-quantum crypto as soon as possible, because if quantum computers are actually 15, 20 years out, then the crypto that we deploy today matters, is going to be attacked by quantum computers. And so the idea is to use something called transitional security or hybrid security, which is to say base the security of your actual system on both something that we have good understanding of now, as well as it seems plausible or reasonable to assume that this piece will be post-quantum. And that in order to break it, you need to break both pieces. So that's what the New Hope work, for example, does. It's a hybrid elliptic curve Diffie-Hellman and ring LWE key exchange. And so, you know, we shouldn't switch to something which might end up being worse than what we have today, but we can easily switch to something which is at least as good today and plausibly post-quantum into the future, and get the best of both, and it doesn't cost all that much. Maybe two times the cost is what it was before. Yeah. But we need more people who know a lot about quantum to learn a lot about lattices and you know, tell us more, right? To show more.
More questions? Okay, if not, thanks.
Okay, thank you.